Starting the recording. And now I'll share my screen.
Can I show my screen?
You should be able to. Let me just make some opening remarks, and then I'll set you up as the, actually, let me do it right now. I'll make you co-chair. So you're co-host, so you should be able to share your screen at the right time. Maarit, I'm also going to make you co-host. I'll make everybody co-host in a minute here, but let's go ahead and get started. We've got the recording started. So welcome everybody. This is the HICSS 55 meeting. Our session, our mini track is case studies of artificial intelligence, business intelligence, and analytic technologies for industry platforms. I'm Jim Spohrer, a retired IBM with ISIP, the International Society of Service Innovation Professionals. I'm hosting the meeting today. The other co-chair, Maarit, Palo is on. Maarit, do you want to say hello?
Hi, hello to everybody, and thank you for submitting your papers and everybody who is also listening. We had a huge success for our mini track, so we needed to really be selective on the ones who will present here. So we had a acceptance rate to hit. So thank you for everybody who presenting and who.
Okay. Thank you, Maarit. And
Here.
I don't see Pekka on, so I think we'll just thank Pekka.
Yeah, Pekka is on also. Are you Pekka here?
Yes.
Ah, there you are. Hi, Pekka.
We have snow in Finland. I was just skiing.
Wonderful. Well, we got snow in the mountains here in California, but no snow down in the valley where I live. Great. So thank you. As Maarit said, it was a very selective this year. We had a lot of submissions, and without further ado, we'd like to introduce the first presentation, an innovative approach to modeling aviation safety incidents. And Donghui, the presenter, is on, so I'm going to stop sharing. And Donghui, do you want to take over the screen and present?
Yes. Yeah. Can I share the screen?
Yes, you should be able to. You're co-host. So there's a little button at the bottom that says share screen. You are co-host. Can you see it? Oh, now you're co-host. I'm sorry. I had been a little slow in making you co-host. Perfect.
Can you see my computer screen?
Yes.
Yes.
Okay, wait a moment. Wait a moment.
And Donghui, I'll give you a 5-minute warning so you'll know when you're coming up to the end of the time for your presentation.
Okay. I come from China. My topic is an innovative approach to modeling aviation safety incidents. This paper is a co-work with University of Louisville. Here is the background. Safety is critical to aviation industry. As the complexity of aviation operations increase, the number of the flight accidents or incidents increase. As a result, effective retrieval and analysis of aviation safety data to reduce incidents remains a challenge. Aviation incidents can be caused by a variety of factors. Identifying true causes is made more difficult by the fact that many relevant data fields have a missing date. Now, common methods for modeling aviation safety incidents. Many machine learning methods are used in predicting causes of aviation incidents. Some people began to use big data, including deep learning and data streaming methods to predict risks in aviation industry. Now, two problems still remain to be solved. One is prediction accuracy rates need to be improved, and another is the runtime of the algorithm need to be reduced. So in this paper, we explore the use of deep learning methods and distributed platform to process the texture data. The data set, we use the Aviation Safety Reporting System, ASRS, by the US National Aviation Safety Data Analysis Center. We use the data field, some text fields, such as the date and the hour of the incident, type of the aircraft personnel, as well as unstructured text data. So in this paper, we use unstructured text data. We identify human factor and non-human factor. In this case, we use will classify presence of the human factors and non-human factors for incidents report. Here is a proportion of the incidents types. In the study, we use sklearn running on a standalone computer and Spark with clusters. Here is the architecture of identification of human factors in aviation incidents. On the left is sklearn, and on the right is a Spark in the distributed environment. First, we use feature selection method to get some structured information from texture data. So two methods, one is TF-IDF, and another is word-to vector, were used to extract the information from the texture data. Another, we use a CNN-LSTM. CNN-LSTM is a neural network. We built a CNN-LSTM neural network model to classify aviation incidents. Here is the structure, the text classification of a CNN-LSTM model. Clusters are formed when independent computers are connected over a network to solve larger computing tasks. In recent years, with the application of a big data technology, Spark is often regarded as the first choice for big data computing platform. Here is a Spark architecture, computer simulation and the results. In the distributed environments, we use one master and 1, 2, 4, or 6 slave nodes. The classification of performance and the running time of classification algorithms for sklearn in Spark in a standalone model and in Spark with cluster in different sample size are shown in the results, where LR, NB, IF, SVM, MLP, and CNN, SLSTM models represent logic space regression, naive-Bayes random forest, support vector machine, multi-layer perceptron, and CNSTM. The classification accuracy rates of a CNSTM are affected by the parameter setting. Through the parameters, the model has best results when dimensions of the word vector selector are 256. And here is other parameters set in the experiment. Here is the results of the model based on ITF, IDF, and on word2 vector. Here is the accuracy rates using different environments. Here's a running time of the several models in different experimental environments. Here we get some conclusions. In the paper, we classified the human factor and the non-human factors from aviation incidents using several models in standalone and distributed environment with different sizes, different data size. Two feature selection methods are used to extract relevant incident type data from the aviation incident reports. 6 models were tested to assess their potential in classifying the incidents in sklearn, Spark with a single node, and Spark with a cluster. Our results show the accuracy of the model in sklearn are higher than those in Spark with clusters. And CNSTM using word vector is best in classifying these incidents. Generally, as the number of sample increase, the overall accuracy rates increase in Spark with cluster using TF-IDF and word2 vector. And the accuracy rates of some model will fluctuate with the data size. The rates of CNSTM model also perform better when data size increase. It shows CNSTM has a better stability and generalization ability. The accuracy rates of the CNSTM model are affected by the word vectors dimension and the number of the convolution canals and the number of the hidden layer nodes and other parameters. In addition, the models using TF-IDF consume less time compared with the models using word2 vector, and LR-IDF and NB-IDF consume relatively less time, while RF-IDF and SVM-IDF consume more time. Although in sklearn and Spark with a single node, CNSTM model consumes more time. The models in Spark with 2, 4, 6 slave nodes consume less time, When processing a small data set, the model in sklearn in a standalone model has obviously advantages, and the models taken less time compared with the models in Spark with clusters. Due to time-consuming communication between data partitions, the models in Spark with a single node and Spark with a cluster will take more time. As the data size increases, the running time the models in Spark with cluster will decrease, which is preferable when processing aviation incidents with a large amount of text data. In the future, we will plan to collect more data to test the performance of the method. And it is meaningful to compare big data methods with more traditional approaches. Thank you for your listening.
Great, thank you very much for the presentation. And now, and I'm putting it in the chat as well. Let's see if we have questions for Donghui. I'll start, but please feel free to unmute if you'd like to ask a question or raise your hand or put your question in the chat. Donghui, can you give some more description of how this might be applied in the real world situation?
Okay. Okay. I think I share. Here is the some background. The data set we come from the aviation safety reporting system. The data set is provided by the U.S. National Aviation Safety Data Analysis Center. In the data, it includes many fields. In the study, we did not use some fields, structured field. We only use the text fields. In the text fields, describe the incident reports. A lot of descriptions. So we use the first use the we use the NLK to get the unstructured get a structure field from unstructured data. In the report, there are several different incidents type. One is human factors, and another is like airport, airspace structure, and menus and aircraft. Other we all we will classify. We all take as non-human factors. So we will classify presence of the human factor and the non-human factor. So
okay,
here,
thank you, Donghui. Thank you, Donghui. I'm sorry to cut you off, but we have to move on. Sorry, I apologize for cutting you off, and but I do want to thank you. And if others have questions, they can put it in the chat, and perhaps Donghui can answer in the chat. But I see Patrick Hemmer, you're on. Would you like to present live, or how would you like to present? The next paper, by the way, I guess I should share my screen. Just 1 second.
Yeah, sure. That's ours. In case you have the video available, I would appreciate it if you just play the video.
Okay. Let me see if I can do that. By the way, our next paper is utilizing active machine learning for quality assurance, a case study of virtual car rendering in the automotive industry. So let me see if I can share the video. Should have rehearsed this in advance. Apologies, I didn't. Okay. Paper. Here's the presentation video.
Hello, everybody. Welcome to the presentation of our paper.
Can you hear it?
Utilizing active machine learning for quality assurance. The case study of virtual car rendering.
Yeah, the voice is available.
My name is Patrick, and I conducted.
But not the
We can't see anything yet.
Niklas and Jakob from Aviation, Germany.
Let me stop
Cooperation with our.
I'll stop it and restart it here when I digging through Windows. Apologies. Screen. There it is. Share. Right. Let's rewind.
Hello, everybody, and welcome to the presentation of our paper, Utilizing Active Machine Learning for Quality Assurance, the case study of virtual car rendering in the automotive industry. My name is Patrick, and I conducted this work together with my Jakob from PST Germany in cooperation with our industry partner, the Audi Business Innovation GmbH, which is a subsidiary of Audi. Over the last years, advances in computer-generated imagery, or in short, CGI, have opened new possibilities for business applications and services for customers. Today, car manufacturers are using CGI technology to create realistic virtual car renderings of all car models, including their derivatives, in all possible configurations which are sold on the market. Virtual car models can be used for advertisement campaigns, which become easily customizable to different markets worldwide. Additionally, they do not require elaborate and cost-intensive photo shoots with real-world car models. Another advantage of CGI is that car manufacturers can offer their customers online car configurators, in which they can configure any offered car model according to their personal preferences. However, representing all car types, including their possible configurations, as realistically as possible without any defects, by continuously updating them, not only resource intense, but also difficult to maintain by manual means. Therefore, in this work, we assess together with our industry partner whether machine learning can be successfully applied to support the quality assurance process for virtual car rendering. Existing quality problems that arise during the virtual production process of 3D car models are, for example, that specific configurations can result in parts of the vehicle not being displayed correctly, which can be triggered by wiring errors of the individual model components. In these cases, black errors appear instead. For example, on the slides, we can see that in the upper row, the Audi Q3 Sportback is displayed in different camera positions without any defects. However, in the lower row, in the exterior front view, the wheel arch linings are not displayed. In the exterior rear view, the taillights are missing. The interior front view, among other parts, the upper part of the gear stick is not present. And in the interior rear view, the driver's seat has no belt. Currently, the quality assurance process on site functions based on randomly chosen configurations and is especially driven by implicit knowledge of which configurations tend to encounter errors. This procedure carries the risk that newly occurring errors remain undetected. Therefore, the goal is to identify as many defects as possible before a car model goes live to avoid suboptimal customer experiences. Before an artifact could be designed, we were confronted to derive design requirements, which we conducted in accordance with the design sense research paradigm. We started our work with an technology partner, and 3 machine learning researchers. First, we found that the company needs the artifact to require significantly fewer images than conventional supervised
No,
machine
there's
learning
no
approaches.
screen sharing at the
The
moment.
reason is that ground truth labels cannot automatically be generated from the rendering engine, and thus manual labeling is inevitable and cost-intensive. Second, as conventional machine learning approaches have demonstrated remarkable results with quality assurance in other domains, the performance of the artifact should be comparable to such a conventional machine learning system on our particular task while requiring less manual annotation effort. Third, even though the manual inspection process is time-intensive, it yields high quality. Therefore, with the artifact, only a small fraction of erroneous images should remain undetected. Lastly, those images that are identified as erroneous should be forwarded to a quality assurance manager for further processing. In order to address the requirements, we select relevant theories from the body of knowledge, which are then incorporated into design principles. We address design requirement 1 to 3 as the kernel theory of active machine learning. That is a machine learning paradigm in which an algorithm can interactively query information from a human expert to label new data points. Draw on uncertainty-based active learning with the goal to identify those instances within the datasets which have the highest contribution to the training process. This should result in a significant increase in the artifact's ability to learn faster. To evaluate the approach, the performance metric that minimizes false negatives is desired, as our goal is to avoid defects remaining undetected. For this purpose, the F2 metric turns out to be a suitable measure. Regarding design requirement 4, we draw from the human-in-the-loop theory and aim to provide the artifact with a forwarding mechanism to a responsible quality assurance manager. The proposed artifact is evaluated with the virtual car model of the Audi Q3 Sportback. We render approximately 4,000 different configurations as 2D images for each of the 4 camera perspectives introduced before. They encompass almost all areas of the car which are visible to customers. All rendered images have undergone a subsequent labeling process. Utilize a ResNet 18 CNN and modify the model for inferring uncertainty estimates by placing a D-relay distribution on the class probability, assigning the CNN's output to its parameters, together with a minimal margin metric as uncertainty measure. For each camera perspective, an individual model is then trained on a small number of annotated images. Subsequently, among the remaining unlabeled images, the ones with the highest predictive uncertainty are chosen for annotation, and the model is then retrained from scratch with a larger annotated data pool. Employ the following 2 baselines: a model trained on all available training data, and a model that acquires new data instances uniformly at random. The active learning process is repeated iteratively and terminated once the performance of the model that acquires the data instances randomly differs only marginally from the one on the entire dataset. Same number of active learning rounds then applies to our proposed artifact. From the visualization, we can derive 3 findings that hold for each of the 4 camera perspectives. First, for all camera perspectives, good performance measures in terms of the F2 metric between 93 and 98% can be achieved. Second, it is possible to train a model with less labeled training data instances by randomly querying training data for annotation, which achieves the same performance compared to a model trained on all available data instances. Both observations might be explained in a way that all images can be rendered in the same data quality, with the car always being displayed in the same position. As different configurations often differ only slightly from each other, this simplifies the recognition for the model even further. But more importantly, we can see that our proposed approach requires even less annotated images compared to random data acquisition, with an image labeling reduction between 400 to 600 images depending on the respective camera perspective. In total, the artifact reaches an average F2 performance metric of approximately 96% while requiring around 35% less labeled training data instances. When we assume a similar detection performance for other car models of the fleet, and when we consider the average time it took the involved experts for data labeling, which was approximately 31 seconds per image, we can calculate a rough time savings estimate of 2 full working days per car model in terms of labeling time. Finally, to sum up our work, in this paper we contribute with generalizable design knowledge by providing precise design principles for the design of active machine learning-based quality assurance systems. In this context, the proposed artifact achieves a promising detection performance measured in terms of the F2 metric of approximately 96%. Regarding the manual labeling effort, using uncertainty-based active machine learning led to an average labeling reduction for the training data of around 35%. As with any other work, this research project is subject to certain limitations, such as the evaluation of the proposed system is currently limited to only one vehicle, namely the Audi Q3 Sportback. Furthermore, it has to be understood as a supporting tool for quality assurance to increase its efficiency and effectiveness, as it does not automate the entire inspection process. For example, the verification of dynamic car model functionality, such as the opening of doors and trunks, are still subject to manual inspection. Future work, the proposed system might be extended to the entire vehicle fleet. Moreover, the system's performance could be further improved by incorporating additional features provided by the rendering engine, such as camera distances of the pixels, better recognize whether objects that should be present are in fact present. Finally, as new configuration options come onto the market at regular intervals, this could result in less accurate classifications over time. For this reason, it could be worthwhile to explore the combination of the proposed system with approaches from the field of concept trace. Having said that, I would like to thank you very much for your attention, and I'm now looking forward to answering your questions.
Thank you, Patrick, Niklas, and Jakob. Any questions for?
Yeah, I have a question.
Please, go ahead.
Thank you. So yeah, the difference is that you showed the artifacts in the pictures that were sort of incorrect. So are those computer generated pictures, or where do the errors stem from?
Yeah, sure. That is from a virtual 3D car engine rendering machine, and they use them, or the manufacturer uses them, for example, in order to, if you think of the online car configurator. So by now, like most of the car manufacturers, they offer users to go online and design or configure their car according to their preferences, and therefore they use those 3D or CGI technology they build themselves for all of the car models of their fleet, those 3D virtual models, and then they try to represent them in all possible configurations that are available on the market. Does that answer the question?
Yeah, I was just thinking, what is the source of the error? Is it from the automation of the process, or is it the human design?
Error source? Yeah, that's a good question. The error source is actually that the individual components, they need to some kind of be wired together. So there's like a logic, and at the moment, or when the project has been conducted, there was no other way to go for going like rule-based through all the possible combinations in order to figure out if there are wiring errors. So, for example, if somebody, when building the car digitally together, and somebody did not wire, for example, the tires correctly together with like seats or something like that in a certain configuration that is on the market, then when you ask, or when you configure yourself this specific configuration and there has been a wiring error, then the specific part of the vehicle, it doesn't show up, and instead there's a black hole that is displayed.
Right. Thank you. Very interesting.
Welcome. Yeah, thank you very much, Patrick, Niklas, and Jakob. And we do have to move on to the next presentation, but please do feel free to add any additional questions in the chat window if people think of a question later. So our next presentation will be automated defect detection of screws in the manufacturing industry. So let me stop sharing and just check with the presenter if I've made them co-host, if they want to present, or if they want me to run the video. I apologize for the interruption last time. I'll not interrupt it this next time. So do we have the presenter? Are you co-host, or are you going to present, or would you prefer the video be run?
If possible, I would prefer if you show the video to avoid technical interruptions.
Very good. I'll do that right now. 2 seconds, Johan. Navigating to the video.
Hello, everyone, and welcome to.
No, I just have to share this.
To our presentation on automated defect detection of screws in the manufacturing industry using convolutional neural networks. My name is Johannes Breitenbach from the University of Bayreuth, and together with Isabelle Eckert, Vanessa, Hermann Baumgartel, and Professor Ricardo Büttner, we are going to present you our work. Let's start with an outlook on what we have achieved. We developed an automatic classification approach based on a CNN model with UJyvaskyla architecture for a reliable classification of defective and non-defective screws. Our model outperforms previous studies with an accuracy of 97.92%. Furthermore, our model is efficient and reliable. Moreover, this study is one of the first to present a CNN model that is trained and evaluated on realistic production images and several realistic defects, instead of using manual classification or deep learning approaches without considering real-world industrial inspection scenarios. Our agenda for today begins with the problem and the research background. Then we will move on to the methodology, followed by our results. Finally, we are going to present our limitations and show directions for future research. Now, Isabelle Eckert is going to present the problem and the research background.
So why is quality control so important? Quality control is necessary during the production process of material components because several defect types can. It is necessary to prevent defective products from getting into the market, and also it is necessary to check the parts with a complex like screws, and also to eliminate defect parts because they can lead to the loss of economic efficiency. Quality control in the industry. The produced parts like screws have a complex structure, resulting in a variety of workpiece defects. This is why the quality inspection of screws is a critical goal. Also, screws are important elements of mechanical components, so those elements must not affect the product in a negative way due to the defects. Defects can cause high manufacturing costs as well as a high amount of rejects. In the past until today, many manufacturers use manual inspection carried out by measuring with calipers and optical amplifiers. This is costly in terms of time and labor. Time-consuming manual inspection can be affected by the level as well as the experience of the worker. So often samples are used for the quality control. It means not every single part can be inspected before leaving the component. A more effective method is the automated defect detection in production processes. As the industrial automation advances, deep learning can help simplify the process of quality control. So based on images, defects in the manufactured objects can be detected, and defect products can be sorted out. In the past, several approaches investigated this problem. So one work used surfaces by only using the top view images, but the screws were mounted. Another work was surface defect detection, but they only considered one defect, and so the location of the different defects was not put into account. Another work used defect detection of small parts for 4 different defect classes, but the 4 classes were separate models, which is not very practical. So this is the first work which investigates if a convolutional neural network approach can classify different defects in screws and defect-free screw images with realistic angles and 5 defect types into a real-world industrial inspection scenario. On to the methodology. First of all, I'm going to present you our architecture. Our architecture is based on CNN network architecture ETT. Consists of 5 blocks, and each with convolutional layer. The kernel size of 3 times 3. For every block, we added a max pooling layer with a kernel size of 2 times 2 to reduce dimensions. We then added a classifier, which consists of 2 dense layers, first one with a filter size of 128, and the second one with 32. We also added 2 dropout layers, each with 50%. Our last layer is an output layer. It is a dense layer with a filter size of 1 because we have a binary classification problem. We therefore use the activated sigmoid, which is commonly used for binary classification. We chose to use the optimizer atom because it combines the advantages of other optimizers, Eckert, and LS-Box. For the training, we used the default learning rate value of 0.001. Our architecture has a total of 40,784,513 parameters. For the fine-tuning, we decided to unfreeze the last 10 layers to make small adjustments. Therefore, we set the learning rate from the optimizer to a very small rate, 0.00005. Trained our model with 200 epochs and a batch size of 32. On to the data set. The data set we used is the MD-Tech anomaly detection data set. The data set consists of 15 categories with a total of 3,354 images of several objects and textures. For example, metal lamp, screw, cable, leather, and wood. The relevant category for this study are the screw images. The screw data set consists of 361 not defective and 119 defect screw images. The screws have several different defects, as you can see on the right. Picture A shows a defect on the screw front. Picture B shows a defect on the screw head. Picture C shows a defect on the screw thread side. Picture D on the screw neck. Picture E shows a defect on the screw thread top. We also added picture F, which shows a defect-free screw. Now for the pre-processing, we decided to use a balanced data set. Therefore, we selected all of the defective screw images. It also shows 119 not defective screw images randomly. We then split the data into a train test validation split with a ratio of 16 to 20, which leaves us with 142 images for the training, 48 for testing, as well as 48 for the validation. Images were resized to 224 times 200 pixels, which is the ideal size for our architecture. They then also were normalized into the range of -1 to 1. We also applied data augmentation, but only on the training images. Augmentation was used to prevent overfitting and also to improve the performance of our model. Use the following functions from data augmentation: rescale and rotation. Now on to the results. Here you can see our performance indicators, and as you can see, our model performs very well. We have an accuracy and balanced accuracy of 97.992% and a kappa of 95.83. This one has a value of 98%. Recall is 97.92. Area under the curve has a value nearly to 1. It has a value of 0.99. The performance indicators were calculated on the unseen test data set, which had 48 images. Here you can see the confusion matrix, and as you can see, all of the 24 defects through images were predicted. We only had one misclassification, and a not defective through was predicted as defect.
Now to the limitations and future work. The main limitation might be the number of images. Only 2 classes could be predicted due to small datasets. Also, the changing lightning conditions were not considered. This might have led to the falsely predicted screw you can see on the right side here. Manually generated effects of the dataset might limit the model too. Also, in real life, several defects can occur on one screw instead of only one defect per screw and image. Also, only one perspective was considered for the screws. The occurrence of dust or dirt on the surface is not extended. And also, the case of cross validation is not performed on the dataset yet. Another limitation might be the absence of external validation, so the model needs to be tested in a real manufacturing environment. So now to the future work. A large dataset could evaluate the proposed model for more specific predictions and would make it possible to indicate errors on machine and optimize the production process. Then enhance the model, anomaly detection could be considered to predict all unknown defects. Also, due to the fast performance, a mobile application would be suitable. To improve the performance, stacking could be useful or more data augmentation could be applied. In the future, experimental work could evaluate the acceptance of the
Now, we would like to kindly thank you for your attention and listening to our presentation on automated defect detection of screws in the manufacturing industry using convolutional neural networks. We hope this topic was as interesting for you as it was for us. Now we are excited for your questions.
A very quick question, Niklas and Johan. I think
yes, Pekka, may I? Yeah. My question is: have you maybe used wavelet techniques to have more accurate model? Do you know that techniques? Wavelets.
Could you please repeat this question? I wasn't able to fully understand.
I'm from Finland. We use wavelet techniques in combination of that convolutional neural networks because it is exact method. It gives more accurate. So just as idea for you.
Yeah, it sounds like an interesting idea.
Yes, yeah. And then what is Adam optimizer? What does it mean?
Yeah,
I have not heard. Is it some
this
gradient method or what is?
Yeah, it is a standard optimizer method. In our study, we have also referenced the original source. There it is described in detail. Currently, it is one of the most widely used optimizers when working with CNN networks.
Okay, some techniques, yes. Did you use software or you have developed by yourself the method?
Could you also please repeat?
Do you use some black box software or you have developed the method by yourself?
Okay.
Yeah, and I'm sorry, we're going to have to move the discussion. We do have discussion time at the very end, and we can do discussion in the chat, but I just, in fairness to the next presenter, I apologize. I have to cut you off, but great questions. Thanks, Pekka, and great presentation, Johannes. And Niklas also has a question in the chat. Thank you. All right, so moving along, our next presentation is investigating the role of technical and process quality in chatbots, a case study in the insurance industry. And I think let me see,
Jim
does the
Jansen.
presenter want to?
Yeah,
present live?
if I could just, yes, please. Jim Jansen here.
Okay. Okay, let me make you co-host, Jim. Thank you. Oops, I'm getting all kinds of calendar pop-ups at the moment, sorry.
No problem.
Technical difficulties. Let's see. For you, there you are. And now you are co-host. Very good. Take it away, Jim.
Thank you. 1 second. Could I get confirmation that you see my screen here? I'm sorry, are my slides showing up?
Not yet.
Not yet,
Okay.
sorry. Your slides are not showing.
All right,
Sorry.
no problem. Okay, let me stop and try that again.
Still no slides.
Yeah, oh, sorry. One more time.
This problem once or twice if the application isn't the front application or you're not showing the whole screen.
Yeah, got it. Here, try this.
There you go. Now you're ready.
Okay, yeah, sorry, I got dual monitors here, so it's a little tricky, you know, so, okay. Well, great, yeah, thank you so much. Our presentation is about research on the aspect of AI in the chatbot industry or the chatbot area. Very active research domain. The TREC conferences have now in their 3rd year of focused on information seeking and the conversational agents. Of course, you know, a variety of spoken and then textual chatbots going on. A lot of industries looking to use chatbots. A lot of consumers both happy and frustrated by chatbots. So, you know, a ripe area for research. I have several co-authors are all listed here. And so let me just kind of dive into the research. My second slide is up.
Yes,
Hello?
it is. Yep.
Yeah.
Okay, good. Yeah. So yeah, let me just give you the bottom line up front. What we did is we wanted to look at human perceptions of this chatbot, a particular chatbot. And so we focused on Emma, which is a chatbot from Finland for a Finnish in the security industry, the insurance industry, which has been really an active user of chatbots. You know, some companies even got to the point of letting chatbots actually process you know, insurance claims. We were kind of interested in customer perceptions. So what we did is did a survey after people visited and interacted with the chatbot, in this case, Emma. We got about just over 200 consumers replying to the survey. We analyzed that on a variety of both technical factors, I mean, how well the chatbot worked, and then the process factors, how empathetic it was, how trusting, and you know, all that kind of stuff. And the bottom line is most people don't like AI chatbots, but it's kind of moderated by the fact that if the chatbot solves a problem, they're okay with it. So I think it points out a variety of aspects with technology that, you know, sometimes our perceptions it's a convoluted mix of stuff going on. So for organizations, I think the takeaway is that there are certainly some advantages with chatbots, but the technical aspects definitely need to be addressed. In other words, it has to be effective, it has to be efficient, the quality has to be high, and then on top of that, there has to be the human element process of, at the end of it, even if they do kind of solve the problem, am I happy with the whole process that went on? So what is Emma, or who is Emma and what is Emma? This is Emma. It is a particular instance of a chatbot technology. And chatbots, at least in our particular definition and our particular research, are an application of AI and machine learning, and they respond to user queries, and they are really the face of a particular organization, at least with that particular customer. So why AI? Well, I mean, it's it's a kind of a constant buzz phrase now. When I was doing my PhD many years ago, AI was very hot then too, and then it tapered off as it went into software agents and intelligent agents, and before that even knowledge systems. So now things have kind of come full circle here because of a lot of technical and machine learning advances. AI does offer a lot of benefits to organizations. It can be more reliable than the human workforce. They don't get sick, they don't gripe about their pay or getting fed or things like that. But there's also certainly some downsides. But overall, a lot of industries are looking at AI and associated machine learning approaches for some optimization and resource utilization efficiencies. Some of the drivers that are also going on are this aspect of not only just the technical part, but this process quality. In other words, this customer relationship management that is the overall interaction with these chatbots, both empathetic as well as efficient, and is it enjoyable and fun, as it is effective. Many times I actually enjoy talking to a person when I call a company, because there is this human element that a lot of times these chatbots just cannot recreate. If you read the paper, we have a fairly lengthy literature review. I'm not going to go into it, but what we do is we build on traditional customer service and customer service technology approaches and compare those to this kind of service technology AI approach, and point out some of the strengths and weaknesses of both. And as shown here on the table, they're kind of counterbalanced for their, in many respects, that the AI technology is very effective and efficient compared to relying on human workforce. But also a lot of times the personal service, the interaction, the emotional reaction, the realism is not there compared to talking to a real person. And we didn't just look at this in isolation. These chatbots are part of a very broad customer service experience, input, process, quality dimensions of this kind of service technology. So you have certain inputs, you have a process that occurs, and then certain outputs. And they're all kind of important, not only just getting your problem solved, but getting it solved effectively, getting it solved in a way that you trust, and getting it solved in a way that you walk away from the experience, very positively. So the particular instance of a chatbot we looked at was Emma for a particular insurance company. And to show an example of the interaction here. As you can see, it looks very computeristic, with this yes, no thing. Emma's based on AI machine learning. It's developed by a Finnish startup called Jian. They have a underlying chatbot development platform that you can develop these intelligent chatbots, your own instance of a particular chatbot. And Emma enables this company to provide basic and sometimes beyond basic customer service real time, 24 hours a day. So again, we were interested in the what the experience of customers interacting with them was. Yeah, specifically we asked after their interaction on the website to participate in a short survey. We got about 225 good responses, and that's what our research is based on. Just some demographics. Most of the survey respondents had been customers for quite some time. About 50% male, so that's pretty good. They tend to, depending on your frame of reference, perhaps a little older or a little younger, but in the 40, to 50 range, with about 60% of them being over 40. So we had several different questions, but they fell both into this technical quality and process quality area. I show them here in this table. Some of the, again, the particulars you can read in the paper, but some of the highlights. Surprisingly, about 40% of the folks said, hey, the chatbot solved my problem, all right, which is completely, all right, which is both good for the company and good for those particular customers. And when we were, that is actually kind of surprising, because a lot of times when people do surveys, they do it to complain, but the fact we had such a positive response is even, even better indicator. However, about 30% of the folks. Yeah.
Just a three-minute warning. Go.
Yeah, I'm wrapping up here. So about 30% of the people reported problems. So overall, about 70% of the folks said that it solved at least a portion of their problem. Again, we kind of report this in the paper, but basically people really don't want to interact with AI, right? Some other interesting findings. There is a relationship between solving ability and the acceptance of AI, and that satisfaction is not only related to the chatbot's ability to solve problems, but also how these problems are solved. So takeaways: 2 dimensions, technical quality and process quality. The chatbot's efficiency is of critical importance, and this process quality is really dependent on technical quality. So even though we like this human emotion thing, it's got to work right first. So if you want more, certainly read our paper. It's a lengthy paper. We go into much more detail, including the literature review, and would certainly appreciate any comments or feedback you have. And with that, thank you very much.
Great, thanks, Jim. Questions, comments for Jim? I'll go ahead and start. My advice on anybody building chatbots is the first thing they make work is when the person says person or agent, that the chatbot know how to handle getting a person or agent and verify that the person wants a person and then get a person. That's, I think, the thing that I've heard people get most frustrated with chatbots, when they want to speak with a person and the system either times out, redirects them to content, or doesn't acknowledge that they're seeking a person to communicate with. So that's my 2 cents on chatbots from personal experience. Any other comments or questions for Jim? Thanks, Jim, and thanks
thank you
for the presentation. We will move to the final presentation, which Rama, I see that you're on, and I think I see Xiao Tong is on as well, an empirical study of factors affecting language-independent models. And since I do not see a recording uploaded, I assume someone's going to present live. Is that correct?
Hi, Jim. I did record the video, so should I just play it?
Oh, yeah. If you can play it, that's even better. I'm sorry, I didn't see it. I was looking on the HICSS website, but please play it if you can. That would be great. Thanks.
Yeah. Give me a minute.
Mm-hmm. Take time. And if there's further questions or comments for Jim, please put them in the chat.
Yeah, somehow Zoom doesn't allow me to share my screen. I'm just trying to figure out what's the best way to share. Sorry, I haven't used Zoom a lot.
Yeah, it's basically, there's a share screen button at the bottom, an up arrow. If you click, if you get the video on your, sort of the front of your applications, and then when you're ready to play the video, then click share screen, that up arrow button at the bottom of your screen. And then you can select an application. You can select your video or your browser if it's playing in a browser.
Yeah.
And I'm sorry, was
I have to rejoin the Zoom because the system, there's the security configuration I need to.
Oh.
Since you just made the presentation yesterday, it's probably fresh in your mind. You just want to give a live presentation that may be just quicker and easier.
Yeah, that's also good.
Yeah, that would be fine as well.
Yeah,
absolutely
sure.
Fine if you want to present it. And
I'm just having an issue to share my screen, so it's not playing a recording. So I need to rejoin the Zoom to update it. Yeah, let me try to.
We'll wait. You have a little buffer at the end for discussion.
Yeah, the pleasures of virtual conferencing. Indeed. Looks like we're going to go this way for a few more months, given how Omicron is spreading.
Yeah. I can't tell everybody how disappointed I am that I'm not in Hawaii.
Yeah, that would have been nice. Google Photos reminds me from the previous years of our HICSS conference photographs, and I was like, oh, wow, that was amazing. I wish we could go back to those days.
Yes,
absolutely,
we have to keep our thumbs up for the next year, or this year, actually. No, next year.
Yeah, absolutely. Yeah, I think we all miss Hawaii. Those of us who've been, for sure. I think I was optimistic around July, August. I took a trip on the East Coast in July when everything was kind of at its lowest, and I was thinking I might get a chance to go to Hawaii again in January, but then of course the Delta picked up and then Omicron, so it's just been better safe than sorry game continue to be played. The right game in my book. All right.
Sorry, I was trying to share and it says host disabled participant screen sharing.
Oh yeah, you. Sorry, when you rejoined, I needed to remake you co-host. So let me do that right now. Okay. There you go. You should be co-host again.
Okay. Okay. Thank you, guys. Yep. Sorry about that.
No worries.
Hello, everyone.
That's great.
My name is Jozef. I'm a manager and a senior data scientist at IBM Watson. Today, I'm going to present a paper, an empirical study of vectors from language independent models. This is a joint work with my colleague from our graduate and my former colleague from Kuhl. Can you guess how many languages we have in the world? It's more than 6,000 languages. And 23 of them are mostly spoken languages, and more than 170 are being used for business. So what is the conventional approach to deliver language of AI models? So this is how we used to do. So we train each individual AI models for each of the languages. And we simultaneously maintain and deploy these models in production and use to serve the applications in the certain languages. So thanks to the recent advance in the NLP domain, so right now we have the option of using the same NLU-based models for different languages. So in other words, we can train a universal models using the input data of the mixed languages, and we can just deploy the single model to serve languages, many more languages in the applications. But the question remains, how effective are these universal models? So in this paper, we entirely investigate the feasibility of multilingual interpretations to build these language-independent models. We use a unified language model pre-trained on the combinations of text corpus from more than 100 languages. And we consider different factors such as task types, language sets, and data resources to evaluate these factors that affect language-independent models. And also, we'll share some of the insights we learned from these experiments to help you develop and customize new language models. So for the task type, we explore whether the language-independent models are effective across different tasks. And in particular, we consider sentiment analysis and named incident recognition. So one is a typical sentence classification tasks, where the other is a sequence labeling task. And for language set, we also explore many different languages when training and testing these models. And also we consider these languages as either high resource, which means they are mostly available and we can relatively easy to get anything data, versus the low resource languages where the large amount of inner data do not often exist. So in the first task, which is the sentiment analysis task, we consider this as a three-class classification problem. We're given a sentence in a target language. We want to predict the sentiment, whether it belongs to positive, neutral, or negative. And in the experiment, we consider three high resource languages, including English, Spanish, Italian, Brazilian Portuguese, Dutch, Japanese, and Chinese, and also 5 low resource languages, including Danish, Swedish, Norwegian, Russian, and Turkish. And for the experiment, we consider several models. And the first baseline is a CNN model, which we all know they are convolutional neural networks. And the second one is Alfred, which is a generative pre-trained language model with task-specific fine-tuning. And the third variant is the monolingual BERT, which basically we train a BERT model using the data from a single language. And for the language-independent models, there are 2 variants. The first one is the model trained with high resource languages, the 7 languages that I just mentioned here. And the second one is it is trained with a mix of the high resource and the low resource languages. Let's first look at the results of the high resource languages. So in the first table, we see we got a significant boost in the performance of around 7% than CNN and 3% than Alfred in English. And for Spanish, we outperformed the other methods by 4% and 2% respectively. And secondly, in the second table, we report that the language-independent model outperformed the English-only BERT model by 2%, and the Japanese-only model by 1%. So even if it falls behind the Chinese-only BERT model, we should be noting that the original BERT model is specifically pre-trained using the Chinese data with this unique character tokenization. So it is still very encouraging to see that the language-independent model is comparable to a specifically customized model. And in the third table, we report the case of zero-shot transfer learning, where we do not include any French data for training. We can still obtain a significant improvement of 6% over the monolingual CNN model trained using French data. which is also very surprising and encouraging. Then let's look at the results on the low resource languages. So if you look at this second column, we demonstrate the effects of zero-shot transfer learning on the low resource languages with an average of 60% accuracy. Since we do not use any of these low resource training data, we can observe that the language model can actually be used to address this cold start problem where no initial model is available for a new targeting low resource language. And furthermore, when we add the few annotated data in each of these low resource languages, we obtain an average of 11% improvement, which is shown in the third column. And this will largely save the cost and time for acquiring annotated data for new target low resource languages, because we only just need a very few labels in these target languages, where we can also reuse the annotated data that are available in the high resource languages. So the second study is performed on this named entity combination, where given a sentence in target language, we want to identify the type of these entities that belongs to a known category set. So we consider French, Italian, and German data in this experiment. And for models, there are two baselines. The first one is by LSTM plus CRF. And the second one is a FLAIR, which is another NLP framework. And the third one is the language independent models pre-trained using BERT. So in the first table, we see that in French, we have obtained a improvement in performance around 10% than BIOS-TM plus CRF, and 7% than FLAIR. And similarly on German and Italian, we also outperformed these competing methods. In the second table, when we consider the zero-shot transfer learning scenario, we train another FLAIR and language models using only the French and Italian data, while we exclude all the German annotated data. So you can see that we are still able to retain the performance of around 60% using the language independent model, where the FLAIR method drops to 20%. So let's briefly review what we found. So while the results demonstrate the values of language models on these two NLP tasks, we found that it is generally more effective on the sequence classification tasks than the sequence labeling tasks, particularly for zero-shot transfer learning. And secondly, since we're using these multilingual BERT, we observe the language independent models are more suitable for these technologically similar languages. And finally, we demonstrate that the language independent models are not only suitable for these high resource languages, but also very effective in low resource languages. We hope the insights gained from these experiments will help you develop solutions and tools that enable better scalability, integration, and operations in many other languages. So the key takeaway is please consider using the language models in your future work, as we show that it solved the cold start problem where no initial model is available for language. And secondly, it saves the cost and time for getting these annotated data for new language, especially when they are low resource. And finally, it also simplified the development process of the new model because you don't have to maintain and deploy every model for every language. Instead, you can just use one model for all languages. Thanks for your attention. I'm happy to answer any questions.
Great, thanks for the presentation. Comments or questions? I don't see any in the chat other than my comments about very nice presentation of the results. It was really clear to see where the improvements were, and you summarized it so well in the takeaways. So thanks for the clear, concise presentation. Now we are into the open discussion time, so but I did want to bring up one last slide here. Let me go ahead and do that. Oh. Okay, so we do have representatives on from some of the other papers as well. Just to fit everything on the screen, sorry I left off the authors' names here, but let me see if anyone has comments or suggestions. Maarit, I don't see your audio on, so if you're talking, we're not hearing you. You might want to use the chat. I do know Maarit had some opening comments for everyone, which was, and I'll echo those, and Pekka, you can join as well. We really do appreciate all of the presenters' efforts in creating a great set of papers. We had even more submitted to the section, so we really do appreciate everybody's efforts. And I still don't see Maarit's audio on, so she's probably having some technical difficulty. Oh, there we go.
Yeah, I technical difficulties because I was, 2 times I was, left over, I needed to go away because, the network was not working. But, nothing more from my side that thank you, because, we were so proud to have so many papers, and now here finally, the top ones. So I was really happy to, finally that we are not even that we are not in Hawaii, but even this was wonderful to hear, the paper presentations. And I can see that Pekka is also here. Anything you want to comment, Pekka?
Thank you very much. Papers were very, very, very interesting, and it was good combination of them, of various applications, and we see how important artificial intelligence and machine learning is nowadays. Thank you.
Yeah, I think over the course of the years, we're definitely seeing increasing quality of the papers in a couple ways. And let me say what I'm seeing. I'm seeing more emphasis on the application and information about the applications. The methodology, the tools seem to be shaking out a little bit more. There still is obviously quite a bit of methodology and tooling in the presentations, but I'm seeing, definitely a shift to the leaning in towards the business impact of the material too. And little by little, that seems to be the shift, the trend that I'm noticing. Let's open it up. Yeah, I will post the recording to IZIP as a sponsor of HICSS, so it'll probably be the IZIP YouTube channel where we'll upload this recording. Several papers do have recordings already on the HICSS website, and I believe it's possible to get access to those. So if you go to the, if you're registered for the conference, you should be able to navigate to the recording. If you can't, let me know, because there are some that have individual recordings. I won't upload those, but I will upload this full presentation to the IZIP YouTube channel. And let's see, any other last words from anybody? Comments? Thanks again to all the presenters. Great stuff.
Yeah, maybe
not-
I say a couple of words. Jim, Maarit, and
Please.
Pekka, this was great.
Please.
So thank you very much.
Good. Very good. Thanks, Krister. And thanks for joining, Krister, as well.
Thank
great.
you, Jim,
All right.
and organizers for organizing this workshop. And amid all the challenges with COVID and all, still hosting a virtual conference and enabling this session. Thanks a lot.
Thanks, Rama. And next time in Hawaii, let's hope.
Yes.
We can only hope still, but let's hope. All right, great. Well, in that case, let me give everybody a few minutes back, and I will get this recording posted probably by this weekend. So have a great 2020. Happy New Year, everyone. And thanks again for all your efforts to make the mini track session a bigger success each year. Thank you. Bye.
And thank you, Jim,
you.
also to you. Thank you.
Thank you.
Thanks. Thanks, Maarit. Thanks, Pekka. Thanks, everyone.
Bye-bye.
Bye. Bye.
Goodbye. Thank you.